XLNet Operation. Overview. Description. XLNet is a generalized autoregressive pre-training method that leverages the best of both autoregressive and auto-encoding language models to capture bidirectional context effectively. Key components. Permutation language modeling. Description. XLNet uses a permutation-based approach to language modeling, where it predicts tokens in a random order, allowing it to capture bidirectional context. Transformer XL backbone. Description. XLNet builds on the Transformer XL architecture, incorporating segment-level recurrence and relative positional encoding to model long-term dependencies. Bidirectional context. Description. Unlike BERT, which masks tokens for prediction, XLNet's permutation language modeling enables it to consider context from both left and right sides of a target token. Steps. Step 1. Description. Pre-training. XLNet is pre-trained on a large corpus of text using permutation language modeling, which involves predicting tokens in various orders to learn bidirectional dependencies. Step 2. Description. Tokenization. Input text is tokenized into subword units using a suitable tokenizer, e.g., sentence piece that handles rare and common words effectively. Step 3. Description. Input representation. Tokens are embedded into vectors, including segment embeddings and positional encodings, to form the input representation for the model. Step 4. Description. Segment-level recurrence. XLNet processes input in segments, maintaining hidden states across segments to capture long-term dependencies, enhancing its ability to understand context over long texts. Step 5. Description. Relative positional encoding. XLNet uses relative positional encoding to represent the position of tokens relative to each other, improving the model's ability to generalize across different text lengths and structures. Step 6. Description. Attention mechanism. The model employs multi-head self-attention to capture relationships between tokens, attending to different parts of the input sequence simultaneously to understand context. Step 7. Description. Permutation and prediction. During pre-training, the model predicts tokens in a random order determined by permutation, learning to use context from all directions to make accurate predictions. Step 8. Description. Fine-tuning. After pre-training, XLNet is fine-tuned on specific downstream tasks, e.g., text classification, question answering by training on labeled datasets related to those tasks. Step 9. Description. Task-specific output. For each downstream task, XLNet's output is adapted to generate task-specific predictions, such as class probabilities for classification or answer spans for question answering. Step 10. Description. Inference. During inference, the fine-tuned XLNet model processes input text, applying its learned representations and attention mechanisms to generate predictions or responses based on the task. Advantages. Bidirectional context. Description. XLNet's permutation language modeling captures bidirectional context without relying on masked tokens, providing a more comprehensive understanding of text. Long-term dependencies. Description. Segment-level recurrence and relative positional encoding enable XLNet to model long-term dependencies effectively, making it suitable for tasks involving lengthy texts. Versatility. Description. XLNet's pre-training method and architecture make it versatile for various NLP tasks, from classification and sentiment analysis to question answering and summarization. Considerations. Computational resources. Description. Training and fine-tuning XLNet require significant computational resources, including powerful GPUs and substantial memory. Data requirements. Description. Pre-training XLNet effectively demands large-scale text corpora, and fine-tuning performance benefits from sizable, high-quality labeled datasets for specific tasks.